Hello, this time I'm going to talk about principal component analysis. This is an unsupervised learning algorithm which is mainly used for reducing the dimension of the dataset. So I will talk about the method, the principal component analysis method, and then I will explain a very interesting application of it, which is called eigenphases. Okay, so PCA tries to identify some direction in which the data approximately lies, and it requires only the computation of eigenvectors. So suppose that you have data about people doing some task, and you have information about how good the person is in the skill of doing that task, so how advanced skills this person have, and also you have information about how much enjoyment, how much fun this person is having while doing the task. So consider these two variables or as attributes or features. So it is common that if some person have fun doing some task, then this person will have a higher probability to do more practice and then to perform and have advanced skills at that task. Okay, so these two variables, skill and enjoyment, we may think of them as variables that are correlated. There is a linear, possible linear correlation between them. So suppose that each of these crosses here represent a person and the amount of skill and enjoyment that this person is having with the task. And what we would like to discover is in which direction or directions. In this case we have here two vectors, E1 pointing towards one direction and G2 pointing to another direction, and we would like to discover this subspace in which the points are more dispersed. And for example, this direction may represent the relationship between the degree of skill and how much enjoyment the person have. And the idea of finding this direction is that we hope that maybe in this direction the data set is easy to understand, and maybe it is easier to find patterns in this direction or directions. So you will see that these directions, like for example in this case, this direction or this vector is the main component of the covariance matrix calculated from this cloud of points, and U2 will be the second component of that same covariance matrix. So consider the following dataset, and this dataset, 5 points, have been already normalized. So normalized in this sense means that the points are, if you compute the mean of the points, the mean is going to be 0, and also that the values that each of the variables x1 and x2 can take are in the same scale. So how can we normalize this data set? So what you need to do is if you have m points, you just compute the sum of these m points or vectors in some dimension, and you divide the result of the sum by m. So it's basically you compute a mean vector. Okay, so this mean vector in each of its components will have the mean corresponding to each of the dimensions of the vector. So in this case, for example, we have vectors in dimension 2. So the mean vector will be composed of two values, the average in the x-axis and the average in the y-axis. Okay, so we need to preprocess the dataset. We need first to compute the mean vector of the points. So we are considering here that we have m points in our dataset, and then we simply sum all of these m vectors. Like in the previous example, we have vectors in dimension 2. M in this case is 5. We have 5 points, and the dimension is 2. So this vector will be a vector in dimension 2, and will be the mean vector of our dataset. Once you have computed the mean vector, you need to replace the original vectors with x minus mu. So you will subtract from each of the points in your dataset the mean vector that you calculated in the first step. And once you have done this, all your points now will be centered around 0. So if you compute again the mean vector of this dataset, the mean vector will be a vector with zeros in each of its components, each of its dimension. Then in the third step, this step has to do with normalization. So what you do is you compute the variance in each of the dimensions of the vector. So in this example of dimension 2, you will have j going from 1 to 2, so only 2 dimensions. So you will compute how much is the variance in dimension 1 of all your points and how much the variance is in dimension 2. So what you do is simply you square each of the x vectors here, because this x is now x minus mu. So we are already computing, by computing the square, we are already computing the variance. And all we need to do is sum all these squares for every point in your dataset and divide it by m. Once you have computed the variance in each dimension, then you will replace again the data points with x over sigma, and by doing this we are scaling all the components of our vectors in such a way that all of them will be in the same scale. So step 1 and 2, you need to do them always. You need to make sure that the points are centered around 0, so the mean vector is 0. And step 3 and 4, they are optional. So if you have a problem in which the variables in each of the dimensions of the vectors are in the same scale, suppose for example that you're talking about images and the grayscale, each of the variables are in the same scale, for example between 0 and 255, then you don't need to normalize, you don't need to execute steps 3 and 4. But for example, if you have a dataset in which the first dimension you have values between 0 and 1, and in your second feature or attribute you have values going from minus 1000 to 1000, they are in different scales. So we don't want to have these differences in the scales because this will affect the result of PCA. So what we need to do is to scale all the variables, all the features, so they are in the same scale, in the same interval, and you need that by executing step 3 and 4. Okay. So in our data set, if we compute the first component of the covariance matrix of the points, you will find this vector here. Okay, and if we project the 5 data points onto this vector, you will get these black circles. And what you are doing, or what you need to do to project the points, if you remember, is to compute the dot product of the point and the vector. Once you have computed the vector, you compute this dot product, and the dot product is going to give a number, and this number represents the distance from the projected point to the origin. Okay. If you compute, as you can see here, in this direction the points have some amount of variance. If you project the points in the second component, which is in this case would be this vector, you will see that the variance here is smaller than in the first vector. Okay. And as we said before, we are interested in these directions in which the data is more dispersed. An important thing to notice when we compute the principal components of a covariance matrix is that the resulting vectors are orthogonal. So you can see that this vector and this vector are orthogonal. In this case, since our points are in dimension 2, our covariance matrix will be a matrix of 2 by 2, and then we can have at most 2 components, 2 eigenvectors. If we were talking about points in dimension 10, you can compute at most 10 eigenvectors. The important thing here is that all these vectors would be orthogonal to each other. Now, we are interested in computing these directions, these vectors that will create a subspace in which our points are more dispersed. Now, if we want to find these vectors, what we're saying is that we want to maximize the variance of the projections, and we will need to choose for this unit length vector that maximizes the variance of the projected points. So we're talking about finding some vectors on unitary length vector U in such a way that if we compute the variance for each one of our points in our data set and we sum these projections and divide by m, if we can find the vector U that makes this amount the largest one, then we have found at that moment the component of our covariance matrix. Okay. Now, if we rewrite this, we can see that first we can get this expression here, and then we can move the U to the left and will keep this to the right, and we will have this expression here. And this expression here is exactly the computation of the eigenvector. If we find some u that maximizes this expression, at that moment we have found the main component of the covariance matrix. So what is a eigenvector and an eigenvalue? So a non-zero vector v of dimension n will be considered an eigenvector of a square matrix n by n if it satisfies the linear equation a times v equals lambda v, where lambda is a scalar, and the corresponding eigenvalue to v. So here we have three elements. V is a vector, lambda is a scalar, and A is a square matrix. A is of size n by n, and V is of size n. What we're saying here is that if we have this matrix and we multiply it by V, the result here is going to be a vector, okay? And this vector should be the same if we simply scale the vector by multiplying it by a constant, by a number, by a scalar, okay? So if V is an eigenvector of A and lambda is the corresponding eigenvalue of that eigenvector V, these two products will give you the same result. So here you will be multiplying the vector by a matrix, and here you will multiply the vector by a scalar. Here there's a graphical example where you can see an eigenvector. So we have this image here, and this image was transformed by multiplying it by a matrix, and the matrix is a rotational matrix, so it is rotating the pixels in this image, so in such a way that this red vector here in the resulting image will be pointing in another direction, but the blue arrow, the blue vector, is the same here. So the blue vector was not changed by the transformation that we applied to the image. So in this case we will consider this blue vector to be an eigenvector of the image which was transformed, but the result was not important or didn't change this blue arrow. And the red arrow, since it was modified, it is not considered to be an eigenvector.